In this video, we're going to be creating possibly the simplest of all thin film structures, an anti-reflection coating. For a basic, low math introduction to some concepts we talk about here, I recommend watching my first video, but if you know a thing or two about light, I'm sure you'll be fine. So what problem are we trying to solve? Well, typically, we've got some sort of window that we were interested in passing light through, and an annoying amount of light is being reflected instead. The application of this most people are familiar with is the anti-reflection coatings available for eyeglasses and sunglasses. When we have glasses in front of our eyes, we are probably interested in looking through them. So any light that doesn't go through and instead comes back can be annoying and is often referred to as glare. Designs for anti-glare or anti-reflection coatings range from simple to complicated. A good philosophy to follow in engineering is to start with the simple and introduce complexity as necessary. So let's design a simple AR coating for some sunglasses. Let's start by defining the problem with some design specifications. I've got some glasses that I like, but they're a bit hard to see through if it's a sunny day. My glasses are made of BK7, a common formula for glass used in lenses. I'll be using these outside, so we're going to be thinking about sunlight. Sunlight is not one color, but we know that it peaks around 500 nanometers, which is approximately green light, so let's use this as a center point for our AR coating. Again, we're going to see what simple gets us, so we'll leave the exact reduction in reflectivity open until we get an idea of the problem. So to start, how bad are our glasses right now? Well, let's take a look at what light looks like coming off this kind of glass. I'll be using an online thin film application called Thinoxide to do my calculations. In full disclosure, I am the creator of Thinoxide, a really useful thin film optics tool that is free to sign up for and use. But feel free to use any design tool you'd like for this if you're following along. Let's go into Thinoxide and create a simple air-to-glass model with no thin films. For the output medium, we'll set it as BK7. This model should be suitable. For the input, we'll be doing this in air. This model should be suitable again, as it's accurate over the visible range. To start, let's put a blank layer with 0 thickness as a placeholder. We'll set up our simulation, 0 degrees, and we'll simulate it over roughly the visible range. If everything looks good, we'll hit simulate. Let's make a new plot. And pull up the result at 0 degrees. And we're interested in the amount of transmitted light, or the amount of reflected light. It would be 1 minus. This isn't terrible as it stands, but it could be better. So how do we improve this? A super simple AR coating can be constructed if we have the right type of material. So what to use then? We can go into Thinoxide and search through some models to inspect what the index is. Let's do this for magnesium fluoride, a super common anti-reflection coating material, and for BK7, our lenses. Let's go to the catalog. Look up BK7 to start. This is the model we are using. Open the model. You can see that around 500 nanometers, the index is approximately 1.52. We'll note that for later. Next, let's look at magnesium fluoride. This model looks suitable for a thin film. We can see that the index is approximately 1.42 at 500 nanometers. To save some time, I've gone and done this already for a bunch of common materials. And here's a table of some approximate refractive indices at 500 nanometers for appropriate thin films. Ideally, an AR coating for a lens in AR has an index that is the square root of the lens's index. For our BK7, that would mean we're looking at material with an index of approximately 1.2. It's tough to get a suitable material this low in the visible range, but magnesium fluoride is about as low as you can get and has some further desirable properties of being easy to deposit as a coating and hard and resistant to scratching. Let's try to use magnesium fluoride then with a thickness equal to a quarter wave. In other words, the thickness is equal to a quarter of a wavelength of the material, calculated simply with this equation, and at 500 nanometers comes out to approximately 88 nanometers. Let's go back to thin oxide and put this layer down. Here's a suitable model for magnesium fluoride. Then, let's set the thickness to approximately what we calculated in the previous slide. Let's check our simulation. And then hit run. We'll plot this alongside our original result. You can see already that with such a simple layer, we are already seeing an improvement in the amount of light that is transmitted instead of being reflected, especially on the design wavelength. At this point, maybe we're happy, or if not for some reason, it might be time to turn to a more advanced design for an AR coating. Many exist that typically involve multiple layers. Note that typically for most lenses, AR coatings are more useful when we're using a higher index glass than basic fused silica or BK7, such as silicon when working in the infrared. I won't be going into these advanced designs in this video, but I want to point out two immediate potential issues with our current design that might cause you to look for a better one. First, our design isn't particularly achromatic, meaning that the way it transmits light varies slightly from one color to the next. You can see this here. The result in practice for our glasses would be that there may be a slight color tinge when we look through them, since some colors come through more than others. More complicated AR coating designs tend to address this. Secondly, recall that we're only looking at how this coating works straight on. At angles, it is definitely going to perform differently. We can simulate this in thin oxide by taking the structure and then simulating over a different angle, also at 500 nanometers. Let's do that now. As you can see, at a sharp angle like 70 degrees, transmission has dropped significantly. Excellent performance over all angles isn't necessary. You'll probably not be looking through the glasses at a 70-degree angle, but this is for you as a designer to decide. That sums up the design and construction of a basic AR coating. In the next video, we are going to be looking at the design of a multi-layer structure in the form of a mirror. Thanks for watching.